So these are the papers, the 5 papers for the second midterm. There is one on heat capacity and entropy changes in processes involving proteins. It's a very interesting paper, and you'll see how this really, the biochemists especially should appreciate it. And these are, this is a practical, very practical paper using the relations that you have been studying so far and talking about how do proteins move and what's really going on. Also, the chemists should be able to, others should also be able to appreciate it. This one talks about a superlattice driven by entropy. When entropy, this is an actual hard sphere binary mixture. And he talks about how the ordering in the material happens completely driven by entropy. The third one is a paper by Gerhard Hammer on conduction of water through the hydrophobic channel of a carbon nanotube. This paper became a super hit around whenever it came out, which was 2001. And it was simulation based, and they saw that it was almost, like a super fluid or something. Water could just run through the center of the carbon nanotube. It was simulation based, but still. So that's the third paper. The fourth one is a sort of a review paper, which talks about hydrophobic effect, which is why oil and water tend to segregate and things like that. It is by David Chandler, who was an expert. He passed away a couple of years ago. And this is really an overview of the field. It's quite nice. Hopefully you will like reading it, and you should be, some of the concepts will be abstract in these papers. I think you have most of the machinery to understand most of the papers. Some of these things will look a bit abstract. You'll be like, I don't know what is this G of R. You'll go have to read a little bit, and that's why you're being split in teams of 5, so you can delegate and assign jobs to people to read. The fifth one is very interesting. It's by, all are very interesting. This one is called Demons, Engines, and the Second Law. This is by Charles Bennett, who actually visited University of Maryland a couple of years ago. And I have a funny email from him. If you remind me, I'll send it to you. I once wrote a computer code for him for something. So this is, since 1871, physicists have been trying to resolve the conundrum of Maxwell's demon, the idea that a creature that can violate the second law of thermodynamics. So this is a creature that sits at the boundary between 2 rooms at different temperatures and selectively allows molecules to go from A to B. So it would almost seem like you're violating whichever statement it was, of second law, the Clausius statement or whatever it was, that heat cannot spontaneously flow from a cold room to a hot room. But what if there is a demon in the middle, and it's a very light demon or whatever, it doesn't need much energy, blah, 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 So, and this demon, this paradox of thermodynamics existed for a long time. Charles Bennett is the one who kind of resolved it. And the resolution actually comes from information theory, from thinking about computer programming and thinking about coding in general. How can you make a code and things like that? So these are 5 papers. I would request you to go through them at least briefly, spend 10 minutes going through them, just forming a flavor, go through the abstract and things like that. And on November 1 or whenever the official midterm will be announced with all the things that you have to do, which will be basically reading the paper, making a plot, talking about the things you like, talking about why you think this paper was cool, or you could comment, I think this was a crap paper, but here are my reasons why I think it was a crap paper. That's also totally fine. You cannot just say, I didn't understand it, hence it was crap. You have to make an effort to understand it and then conclude. But you'll be in teams of 5 and read it so you can make a case with your team as to which paper should you pick. If you don't pick it, one person in the team who reads the papers and like one paper will come and steer all of you away with the paper that person likes. So make a case, and then you have to argue within your team of 5 as to which paper you will pick. Any questions about this?
Are they posted on Slack right now?
They are posted on Slack. Let me reshare it again, and I will also send an email.
Okay.
They are posted on Slack in a thread because I didn't want to complete.
I'm looking under general right now. I can't see.
Yeah, I will share it. That's one more.
Okay.
And maybe one of you can pin it, or I can pin it, because there will be these 5 papers. And there is still time. If any one of you is interested that I really want to study this paper, and I think the group, the class as a whole, some people might be interested. You might find a paper that only you are interested in and no one else cares about it. Then what's the point, right? So if you can find a paper that you think others could be made interested in, so then we can share that also. Okay, any more questions? Okay, let's do a very quick poll. This is not a pop quiz. I am going to do a very, very quick poll to ask you to get a sense of something. Do you know what? Okay. Okay, here's your poll. The question is simple. Do you know what is a chemical potential? Yes or no? I just want to see how many of you have seen the term before. Oh, the no's are winning slightly. Okay, I have a sense. We don't need it from everyone. It's 50-50, plus minus, as a function of time. 46%, 54%. Cool. So the 54% of you who don't know what's a chemical potential are in for a treat. This is going to be one of the defining days of your life, I think. The first day you learn about chemical potential. Nah, it's okay. It's confusing, and hopefully I can do justice to it. Okay. So the reason why we will start talking about chemical potential today is because all of the things we have done so far, we have assumed constant potential system, constant composition systems, right? But who really works with a constant composition system? Maybe you're looking at pure iron or pure argon or something like that, and it's constant composition. But most of the time, you don't have a constant composition. You have a bunch of things existing in the system. Now, it's possible that these things don't change. Constant composition doesn't just mean this could be just a single component system, just one component, or it could be many components. It could be many components, but their relative ratios, their ratios do not change, right? So let's say you have 5 moles of, why is the pencil turn this? You have 5 moles of A and 10 moles of B and 11 moles of C, and sorry about that, let's stop it again. So you have 5 moles of A, 10 moles of B, 11 moles of C, and nothing changes. You just stay with what you have. So that's also chemical constant composition system. But most of the times, this is not true. Does anyone have a sense as to when might a system, let's made of 5A, 10B, 11C, why might it not be a constant composition system? Can you think of a scenario?
If there's a reaction between like A, B, and C, like a chemical reaction?
Correct. There is a reaction between A, B, and C. Or if you are connected with a reservoir which has lots of A, right? And it's pumping A into the system. You know, it's an open system where mass can go in and out. For example, in a solar cell or something, you know, you're thinking about photons in the system. You think of photon as one of the components. The number of photons is constantly changing. So chemical reactions is the simplest example, but in general, the number can keep changing in many possible ways. So it's important to study what happens there, because most of the times we will be dealing with this. How do we do that? So we will start with how it gives free energy. There are 2 reasons to start with it. First of all, constant temperature and pressure is a popular scenario that we experience, and my screen has frozen, which is truly terrible. I tried something alternate today, which is to just do it from Zoom, but without share, and that wasn't working. Sorry. All right. Well, I can't help that. Okay, now it's recording. I want to make a point that in the few minutes that did not get recorded, I explained as to why AI bar is not equal to mu I and why HI bar is not equal to mu I. Only GI bar is equal to mu I. Okay? I don't know how this happened, but that's fine. There was some missing video. Good thing you pointed out. So we can finish this one. So we have these two equations and now compare. They are both DG, right? So compare 8 with 9. I will make a point about that part being important for midterm at the end of the class when all of you leave, so it's in the recording, okay? So there is no unfair advantage. There is at least one student who is in Thailand right now. I cannot expect that student to attend the class, and I think there are many more outside. Compare 8 with 9. What do we get? DG is equal to DG, so we just compare the right-hand side of both. This and this will cancel out, right? And we will be left with I and I d mu I is equal to V dP minus SDT. And this is known as our Gibbs-Duhem equation. Gibbs-Duhem. A more popular form of Gibbs-Duhem is at constant pressure and temperature, summation I Ni d mu I is equal to 0. So that's our Gibbs-Duhem, and next class we will start with something that really builds up on the concept of chemical potential, that is phases and phase diagrams. So for the material scientists in the class, the next few lectures are going to be cakewalk. That means you should still attend and help your classmates. Some of you are going to struggle. It's not going to be very math heavy necessarily, but it will be a slightly different type of concepts. So the material scientists, I request you to help your other classmates with that material because you have done phase diagrams before. And the reason why we could derive this followed from an important thing that I mentioned. Today we talked about partial volumes, and I think the recording missed out on that, and I'm sorry about that. When we defined the partial volume, yeah, sure. So that's what I'm doing now. And if you leave, you leave. I will be recording it anyway. I think my next Zoom meeting, I have 9 minutes. So what we did here was to realize I'm going to capture the material that was not recorded. So I'm just going to work from here again. I don't know when exactly the recording stopped, but this is all stuff in the books. This part is where it starts to get complicated in the books. So we have some extensive quantity G, Gibbs energy, or it could be H, or it could be volume. Volume by G is not extensive, that is an intensive quantity. So if G is an extensive quantity, then at constant temperature and pressure, we can write down G as a function of N1, N2, N3, Nn. So now it means the total derivative dG can be written as partial G by partial Ni, constant T, P, because we have specified constant T and P, and Nj not equal to Ni multiplied by Dni. So this quantity, partial G by partial Ni at constant T, P, Nj not equal to Ni has a name. It's called the partial molar of Gibbs free energy. Similarly, we could have done a similar thing for volume, which is another extensive quantity. It will be partial volume by partial Ni at constant T, again constant Tp, Nj not equal to Ni. In this case, it would be partial molar volume. We could do it for Helmholtz free energy. It could be partial molar Helmholtz free energy. However, for Gi bar, it is also equal to mu I from equation 1. Why? Because in equation 1, you have seen mu I is defined as constant temperature, pressure, Nj not equal to I. This is for any other quantity. For V, it doesn't make sense. But if you go to A, for example, this is not equal to mu I. Because if you go and look at equation number, which one is it? Equation number 4. If you check equation number 4, there you don't have constant temperature and pressure. You have constant temperature and volume for A. So mu I is equal to partial molar of Gibbs free energy. Mu I is not equal to partial molar of the other quantities. So we can proceed from here. We can write down dG as summation Gi bar dni. For a two-component system, this means dG is equal to G1 bar dn plus G2 bar dn2. Remember, G1 bar and G2 bar are intensive. They do not depend on N1 and N2. These were defined as partial G by partial Ni. The number dependence has gone away. So we can now integrate this equation, both sides. When we integrate it, the subtle idea here is that since G1 bar and G2 bar are intensive, they don't depend on N1 and N2. They can be taken out of the integral. So this becomes G is equal to G1 bar N1 plus G2 bar N2. It just falls out of the integral, or in general is equal to G is equal to summation I, Gi bar Ni. Same relations will apply to H, to V, to A, to any extensive quantity where all you are doing is to define something which is a partial molar. Once you have this partial molar, for G, this happens to be mu I. So now we have a separate relation for G. We have G is equal to summation I is equal to 1 to N, mu I Ni. We differentiate this, we get dg is equal to summation I mu I dni plus ni d mu I. We also have dg is equal to vdp minus sdt plus summation I mu di di. We compare these two and we get our Gibbs to Hem equation. So for those of you who are watching the videos and were not in the class, you must have discovered a break in the middle of the class, but I have recapitulated all of that was there in the break. If something is not clear, please ask me on Slack. And otherwise, see you on Friday for phases and phase diagrams. Thanks.
Can I ask a quick question? So are all of the partial molar, I think someone might have asked this already, but for all of the partial molar things like A bar, I, G bar, I, all that stuff, is it always in terms of T, P, and N? Okay, so that's why you wrote it, that's why you wrote A that way instead of with a V, and that's why it's not equal to mu I.
It's a simple thing, right? There is nothing profound. But it confuses because you think, why could I not derive a similar Gibbs to Hem equation? Why could I not derive a Helmholtz to Hem equation, right? You see why you can't do that? The reason why you can't do that is because you won't be able to write A is equal to summation I mu I Ni, right?
Mm-hmm.
That is not true. It used to confuse me so much. Why can't we do that? The reason we can't do that is because this is not true. Mu I is only the other thing.
I was about to ask the same question because, like, wait, equation 4 has, like, it tells you that the partial is equal to mu I, so why isn't it when it's A bar? But if it has to be T, P, and N, that makes more sense because it doesn't match.
It's all about, that's why you see thermo is really all about multivariable calculus. Okay, see you all on Friday. Bye.
Thank you.